In this video, we're going to learn how we can prove simple conditional statements using a direct proof. This is the most basic type of proof and it's one that we're going to use a lot in this course. So let's take a look at the first example. So we have a theorem that tells us that the sum of two odd numbers is an integer number. So it says that if x and y are odd, then x plus y is even. And remember, here we have the hidden quantifier, right? For every integer x and y, if x and y are odd, then x plus y is even. And here we have two parts. We have the hypothesis, which is that x and y are odd, and we have the conclusion that x plus y is even. So the hypothesis is what I am going to assume is true, and the conclusion is what I need to show. That's my goal. That's what I want to get, assuming that the hypothesis happened. So before we start doing the proof, we need to make sure that we all agree on the definition of even and odd number. So if we have an integer number, we say that x is even if there exists an integer number m such that x is equal to 2m, and x is odd if I can find an integer m such that x is equal to 2m plus 1. So what in this language, now what we say is that, well, what do we know? We know that x is odd, we know that y is odd. What does it mean in terms of the definition of odd? Well, it means that I can write x as 2m plus 1 for some integer m. That's why I'm saying there exists an m such that x is equal to 2m plus 1. And y is odd, well, it means that y can be written as 2n plus 1 for some integer number n. And check this. I used different letters for the n and m. So x is equal to 2m plus 1 and y is equal to 2n plus 1. And the reason for that is that if I use the same letter in my proof, I could be confused and end up thinking that both x and y are the same number, right? If I say that x is equal to 2m plus 1 and that y is equal to 2m plus 1, well, boom, that would be the same number, and that would be wrong because x and y don't have to be the same. So be careful, we're picking two arbitrary odd numbers, so we need to use different letters for that existential quantifier there. And then what is my goal? What is what I want to prove? Well, I want to show that x plus y is even. And going back to our definition, that means that I have to find some integer, I'll call it q, such that x plus y is equal to 2q. Again, notice that I use a different letter from the ones that I use for my x and for my y, just to make sure that there is no confusion. Now that we have all the bits here, look at this. I wrote what I know, those are my assumptions, and I wrote what I want to show, my goal. I wrote them. This is not a proof, of course, I haven't connected the dots, but it helps me understand exactly what I'm allowed to use and where I have to end. So let's take a look at this. How can we write the proof? Well, the first thing is we need to assume that x and y are odd integer numbers, right? We're going to start by assuming my hypothesis. And then, okay, we know that by the definition of odd number, we can find two integers m and n, such that x is equal to 2m plus 1 and y is equal to 2n plus 1. And I want to conclude something about x plus y, so I need to build x plus y. Well, x plus y then would be 2m plus 1 plus 2n plus 1. And now, well, you know all the properties for real numbers, you know how to add, you have commutativity, associativity, all these things that you know from before. We're going to talk about them later in this course, but for now, you can assume that all the rules of the game are true. So we're going to massage this expression to make it look like what I want. So here I can regroup things, and we end up with 2m plus 2n plus 2. But now, remember, my end goal was to end up with x plus y is even. So x plus y is equal to 2 times something. But here you see we have 2 everywhere. We have a common factor of 2. So then this can be written as 2 times m plus n plus 1. And that's great, because if I take q equals to m plus n plus 1, then we have that q is an integer because, well, the sum of integer numbers is also an integer, or like that integers are closed under addition, which is something that we're going to talk about later when we talk about real numbers. And, well, x plus y is equal to 2q. So that's exactly what we wanted. X plus y is even, and that completes a proof. And that's it. We've done already our first proof of a conditional statement. And we'll see that we have many more beautiful proofs to come.